Hello, how are we doing today? We're going to try this again. Yesterday I did an amazing job of teaching this lesson, and then I got home last night and I was getting ready to upload that video, and there was no sound, and I realized, oh my goodness, I had muted the mic. Never done that before. Don't know what happened. So, and you missed it too because I was wearing my lucky Albert Einstein tie. Today I'm rocking the Indiana GearUp tutoring program, charcoal gray polo. So hopefully it'll be just as good as yesterday's lesson. But I'm not muted. I can see in the corner now. There's a little picture of a microphone. I didn't notice that yesterday. So here we go. We're going to jump in. We're jumping into Chapter 2 or Unit 2, Section 1, and some more good news. If math is not your particular cup of tea, this unit might be your unit because there's not going to be a whole lot of math in it today. Matter of fact, today when we look at these patterns, will probably be the most math of any section in this unit. So if you're not, that's not your thing, this could be your chapter. So we're going to jump right in. Again, some apologies on the test. You just got to bear with us. All of us teachers, we're doing some new things this year. You guys are learning online. A lot of things are going on. Just everybody be real patient. As far as me and submitting assignments, just a quick rundown of what I've noticed. We're forgetting to submit the assignment on the answer sheet, okay? And I know that caused some confusion at the beginning, and I'm getting the in-person people are figuring it out. Hopefully you online people are going to figure it out too. There's almost always two documents. There's the worksheet, and right next to it there's the answer sheet for the worksheet. So don't submit it on the worksheet itself. Submit it on that Google Doc, that answer sheet, and at the top, super important. Matter of fact, I'm starting to take points off if you don't do this. You got to put what period I have you. It makes things so much better if you do that. Faster. I know you all are wanting to see those grades. I'm getting emails from you saying, hey, I turned this in and all this stuff and I haven't got it in there. Another thing on that, if you turn stuff in late, I'm not going to lie to you, it doesn't become my first priority anymore. So I know when you finally turn in an assignment, you're all excited about it. You want that grade to pop in there immediately. No, it doesn't work that way. It just doesn't. I've got a laundry list of things I got to do, and I know that's not your problem. But when you turn in an assignment late, that's down low on my laundry list of things I got to do. I got people who are trying to get into the test and they can't, and I'm fixing that. By the way, good job with that. Please remember when you're taking the test, you can't click any other tabs. I forgot to put that in the instructions, so I'm not too upset that people did it. The people who did it twice, I don't know about that, but when you click on another tab, it kicks you out of the test, so don't do that. Have your own calculator ready. All right, enough on that. Let's jump in and learn some stuff about inductive reasoning and patterns, all right? So we're going to learn two different types of reasoning in this class. The first one is called inductive reasoning. It focuses on noticing patterns of events that happen or things that happen, and then from that, noticing that pattern, we make a prediction about what we might think happens in the future. Imagine a kid who finds a penny for the first time and starts flipping it. Imagine if that kid flipped it 5 times in a row, and each time it landed on tails. He might think, oh, okay, there's a pattern. Every time I flip this little coin, it always lands on tails. Maybe it always lands on tails when I do it, and we know that it doesn't always, but if the first 5 times you flipped a coin and it always landed on tails, you could think that. And that's a pattern. All right? Now, what that child did is they made a conjecture. All right? They flipped it 5 times and it always landed on tails, so they think, well, every time you flip this thing, it lands on tails. They're making a conjecture. It's a fancy word for a prediction using inductive reasoning, all right? In science class, you might call this a hypothesis, an educated guess kind of thing. In geometry, it's a conjecture. Now, down here at the bottom of the screen, you don't have to copy this, but just follow along with what's going on. I got a weekly schedule here: Monday, Tuesday, Wednesday, Thursday, Friday. And if you notice, there's a lot of hitting with snowballs. Okay, so we're going to go back to January of 1982. I was a sophomore in high school over there in the Ville, going to good old Moore High School, back when it was really a solid school, competing with all the other schools academically and in some sports. And I'm walking home from school, all right? Here's a week worth of me walking home from school. Now, in inductive reasoning, the same thing has to happen each time. I shouldn't say the same thing. The same situation has to happen each time. Like maybe I'm flipping a coin. Boom, boom, boom. I'm flipping a coin each time. Or maybe I'm rolling a die each time. Well, in this situation, I'm walking home from school and I have to walk down the same street each day. So on Monday, I'm walking down this street, and as I come up to this yellow house on the left, boom, I get hit in the face with a snowball. All right, that'd be kind of random. You'd be like, wow, I wasn't expecting that. So then on Tuesday, when I'm walking down that same street, I see the yellow house coming up. You know what would be going through my mind, because it just happened 24 hours earlier. I'm coming up to that yellow house and be like, oh man, remember yesterday? I got hit by a snowball, and while I'm thinking that, boom, I get hit with another snowball on Tuesday. Man, okay. So that's kind of weird. Now, on Wednesday, imagine, I'm walking down that street, I'm coming to the yellow house, and I'm thinking, wow, 2 days in a row. I'm kind of watching out now, like, am I going to get hit with a snowball again? I mean, 2 days in a row, it happened, boom, I get hit with another snowball. 3 days in a row. Okay. Now, this is usually about here where my students say, hey, why don't you go a different way? Now, in the real world, I could maybe have done that. But in the inductive reasoning world, the circumstances, the situation needs to be the same each time, right? So in this example, I'm forced to walk down that same street past the yellow house. And Thursday, I might have my 3-ring binder with all my geometry notes in it. Well, I was actually in Algebra 2 in 10th grade, but I got my binder up. I'm trying to protect myself, and no matter what, though, on Thursday, boom, when I walk past the yellow house, hit with a snowball. Bam! So now, at this point, stop and have you pause and think, what's going to happen to him on Friday when he walks past the yellow house? Is he going to get hit with a snowball again, or something different going to happen? Well, take a few seconds to think about it. All right, what do you think? Well, today I have the luxury of telling you what some of the people thought. Some people said, yeah, he's going to get hit again. He's walking down that same street. It's happened 4 days in a row. Why wouldn't it happen on the 5th day? Boom, they could be right. So I could get hit by a snowball. But then I told my students, I said, hey, what are some reasons why I might not get hit by a snowball on Friday? And we had various answers come up. One student suggested that the kid, whoever's throwing the snowballs at me, got in trouble after he did it on Thursday, and he got grounded, and he couldn't throw it at me on Friday. And then the most logical answer came up. Finally, somebody said, well, the snow might have all melted, and there might not have been snow on the ground to make a snowball on Friday. And that's another perfectly good thing. So the main thing I want you to get out of conjectures and patterns is this. Conjectures do not always come true. Maybe I would get hit Friday by a snowball, maybe I wouldn't. So patterns don't always have to hold up. That little kid who flipped that penny and got tails 5 times in a row, is he always going to get tails? Unlikely. That would be crazy. There must be something wrong with his coin if he always got tails every time. But patterns do happen. Sometimes they continue on, sometimes they don't. We got some movie showtimes. We're going to pretend like this pattern does continue on. You got some, this must be a little kiddie movie. They show it early in the morning. It doesn't seem like it's a very long show. But the first showing's at 8:30 a.m., then they have another one 9:45 a.m., 11 a.m., and then it jumps up to 12:15 p.m. There is a pattern there. And if that pattern holds up, I would have you try to figure out what the pattern is between all these different showtimes, and then make a prediction on what you think the next showtime would be. So go ahead and pause it, take a few seconds, I'll step out of the way. All right, welcome back. What did you notice? Did you notice the pattern was, and I'll go ahead and tell you, the pattern you should have got was there's an hour and 15 minutes in between each of these show times, kind of like you had on your first exam, hour and 15 minutes. Hopefully that was plenty of time for you. Like I said, that was a 45-minute test, so hopefully everybody easily got it done in an hour and 15, I would hope. And yeah, that's what's going on here. From 8:30 a.m. to 9:45 a.m., that would be adding an hour and 15 minutes. Same thing here. From 9:45 to 11, that would be adding an hour and 15 minutes. And then 11 to 12:15, that's probably the easiest one to see. That's definitely adding an hour and 15 minutes. So hopefully you saw that pattern and you added an hour and 15 minutes to 12:15, and that would put you at 1:30 p.m. All right, so notice a little pattern, you make a prediction, and hopefully that was your conjecture, 1:30. All right, let's move on. Okay. Ooh, back in the olden days when I was a kid, we had colored pictures when I was a kid. I mean, the black and white photos were faced. Do y'all know what photos are? Like the little piece of paper and has like a picture on it. It's not on your phone anymore. I'm old, but I'm not old where they were all black and white. Matter of fact, there's not very many black and white pictures of me. There's a few. I've seen a few, but so I'm not that old. I'm not black and white pictures old. I'm color pictures. And I don't know how I got onto that, but I'm talking about in the olden days, we didn't have cell phones. So like if you went to the doctor's office and it wasn't your turn yet, you're sitting out in the waiting room, we had to do this thing that teenagers today hate. It didn't bother me too much as a teenager, but it seems to bother teenagers in this generation quite a bit. And we had to do this thing called wait. All right, and we didn't have a cell phone. We couldn't play Happy Wheels or whatever y'all do on your cell phone, or social media, or Snapface, or Insta Chat, or whatever. We had to just wait. So when I would go to the doctor's office, I would always take a box of toothpicks. Isn't that what you all do? I take a box of toothpicks. And on this one particular doctor's visit, I made a square out of toothpicks. Oh, by the way, you don't have to write all this. Please just watch along. If you want to pause it and then copy it down later or whatever to have nice full notes, you can. But you don't feel like you need to copy it right now. Okay. So I make the first square, and obviously that would take me 4 toothpicks or 4 sticks. I've got written here. And then I'm still kind of waiting for my turn at the doctor's office. So I take this original square and I put like a layer around it. I add like another, I don't know what you would call that. I'm just gonna call it layer. And when I do add that second layer around it, I notice it takes 10 toothpicks to do that. And now I'm still waiting, so I take this second figure and I add another layer around it. And when I do that, that takes 18 total toothpicks. All right, are y'all seeing what's going on here? So it's still not my turn to see the doctor yet, so I take this third figure and I add another layer around it, and that takes 28 toothpicks. All right, now being a math person or a numbers person, I notice a little pattern going on with these numbers. All right, see if you can notice that pattern. Hopefully you can. Give you a few seconds to do that. So I went from 4 to 10 to 18 to 28. Now without drawing another layer, because that's what I'm going to pretend like I'm going to do in a minute, draw another layer around that, I'm wondering if there's a way I can make a prediction at how many toothpicks it would take based on previous examples. All right? So take a few minutes, take a few seconds and try to figure out what you think that would be. And I'm going to pretend like that time has passed and you all said, okay, well, when we went from 4 to 10, that was an increase of 6. We had to add 6 toothpicks to get to that. And then from here to here, I went from 10 to 18. That's an increase of 8 toothpicks. So 6, 8. I wonder if the next number is going to be, we'll see, 18 to 28. Oh my goodness, that's an increase of 10. So it's going up, but it's going up and going up by 2 more each time. So if this pattern holds up, plus 6, plus 8, plus 10. The next one you would think would be plus 12. And so my prediction would be to make this next figure where I add another layer around this, it would take me 28 plus 12 toothpicks, 40 toothpicks. And I'm not going to draw it just to save time, but trust me, that would be how many toothpicks it would take. So that pattern does hold up, and if you keep adding layers, that pattern will keep holding up. All right? Questions on that? I hope everybody conjectured that it was going to be 40. I hope you did. If not, maybe this one will be a little more easy. So now we go from me being a child at the doctor's office to me being this old 53-and-a-half-year-old man at the doctor's office. And now I go to the doctor and I have the follow-up appointments. He wants to check my, my vital signs, or what vital sign, I don't know what I'm talking about. Blood pressure, cholesterol, that stuff that old people have to deal with. So he wants to check it at, obviously, multiple times, but I forgot what the last one was. Maybe I couldn't read it, or I didn't pay attention, I didn't write it down. But I'm thinking to myself that there's probably a pattern from these months. These are months, by the way: December, May, October, March. And I'm thinking there's probably some pattern to this. And what is that pattern? And if I could use it to predict or conjecture what the last appointment is. So you take a look at those months, December, May, October, March, and make a prediction what you think that last month would be. All right? Okay. Well, from December to May, here's what I'm gonna physically count them. Now be careful, don't do the classic December and count that as a month. No. I'm on December right now. We're saying we're on December. So the first month would be January, February, March, April, May. So between December and May, there's 5 months have gone by, right? And now let's check and see if that holds up from May to October. So I'm at May. Let me see if I remember my months. May, so then I would go June, July, August, September, October. Again, yes, that is 5 months later. So the pattern must be these appointments are every 5 months. We'll chickadee check it by going from October to March. So October, November, December, January, February, March. Bam, it's holding up. So hopefully everybody at home made the correct prediction or conjecture of what the last appointment month would be. And it would be, if we add 5 months to March, let's see, March, April, May, June, July, August. So hopefully everybody conjectured that the last month would be August. If you did, great, you're starting to see it. And if you're not, just keep trying them. We're going to have some mathematical ones coming up here in a moment. And what I would tell people is, this happens all the time. Like, I have kids in class who, like, they always make straight A's in math, and they've, never got less than an A on a math test or whatever. And sometimes those students, like, struggle with these. They don't see them. And then they look around the classroom and they see other kids who aren't so awesome at math, who are getting them like this. They're like, oh, they're firing off answers like crazy. And they think, oh my goodness, what's happened to me? Am I not smart anymore? No. Patterns, it's just really weird. Some people just, their brains are wired and they see patterns like immediately. I'm one of those people, I can see number patterns pretty quickly, and you'll say, well, you're a math teacher, so that's good. And I'm like, yeah, but there's, some people just really see them fast, and some people don't see them as fast, and it's not really a smart, not smart kind of thing. It's more just like, some people see this, just like, playing a musical instrument. Some people pick it up and they can start playing it like crazy. Like my son, he's never had a piano lesson in his life, and he can hear some song and he starts plunking it out on the piano without any lessons. And me, I could probably take piano lessons for years and not play as good as him. So it's just one of those things. So don't get frustrated with that, is what I'm trying to say. It'll come. I'm not going to do any patterns that are like impossible for certain people to see. I would hope not, at least. So here we go. Okay, as promised, here's a few number ones. And then, check this out right here. Challenge level on this one. Now, for you guys playing at home, that doesn't mean too much to you all. It's just probably going to be a harder problem. But the guys here at school, the in-person people, they know that if you get a challenge level problem right, you don't just get one of my juicy smiley faces. You get 1.5, man. And we had a new record set today, man. I forgot to. Shouldn't say the person's name or anything, because, yeah. All right. But we had a new record just broken today. The new record is up to 8.5 smiley faces in one class period. It's pretty awesome. Okay, enough on that though. So we got some numbers, sequences, or patterns, or whatever you want, and we're going to pretend like they hold up. The pattern continues, so we can make some predictions about what the next number will be. So while you're writing that down and thinking of it, I'll give you some hints that I always think of. When the numbers go up, like if you have a number pattern and the numbers seem to be going up, you should try, is it going up by addition or is it going up by multiplication? Because those are the two main ways the numbers get bigger, right? Same thing with when the pattern's going down. If the numbers are getting smaller, so you should think of, okay, the numbers are getting smaller. Am I subtracting? Am I dividing? And if you try those two things, you usually can figure it out. So hopefully I'll give everybody a shot to do this one. We got a 10, a 4, a -2, a -8. Those numbers are definitely going down, right? I started at +10 and I'm down to -8. So probably there's either some subtraction or dividing going on. And so you might look at that. So again, we're going to pretend like you did. And hopefully everybody made a prediction. Filled in a number right here, and again, you should be doing that. You should not be watching this like you're watching Breaking Bad or something like that. You should be pencil and paper, maybe a calculator, pausing here and there, trying the problems before me. Don't passively watch this with a bowl of chips and soft drink or whatever, and cell phone there. You don't want any of that stuff interfering. You should be actively trying this stuff. So I'm noticing the numbers are going down, so it's probably a division or a subtraction situation. I look at the first two numbers, and that's not an easy division thing. From 10 down to 4, you could divide 10 and somehow get 4, but it's not a nice smooth division like divide by 2 or something like that. So I'm going to forget about division and move to subtraction. So 10 down to 4, that would be a subtract 6. And then I chickadee check it by subtracting 6 again, and sure enough, 4 minus 6 would put me at -2. And so that looks like it's the pattern. And yep, -2, take away 6 would put you at -8. So hopefully everybody made your conjecture that -8, take away 6 more would put you at -14. All right, that was a pretty straightforward one. Hopefully everybody got that. This one's a little weird. If you ignore the signs of the numbers are increasing. If you're ignoring the signs, you got 1, 2, 4, 8, 16. So numerically, ignoring the signs, it's increasing. So this, you should be thinking like addition maybe, or some kind of a multiplication as your hint. But then the fact that these numbers are going back and forth from positive to negative to positive to negative to positive, that's probably will give you an idea of what this next number should be sign-wise, since there seem to be vacillating back and forth between positive and negative. And that was our SAT word of the day. You can't see it, it's off screen, but yeah, today's SAT word of the day, because of this, is vacillating. Good word. It means go back and forth, one side or the other. Positive, negative, positive, negative. So, and then getting bigger. So hopefully everybody figured out what's going on here is a multiplication, but by a -2. See, 1 to 2, that's times 2 times 2 times 2 times 2. But since the signs are switching back and forth, positive, negative, what's happening is we're multiplying by -2. Now, we don't use a big X for multiplying anymore. You all know we use X for a variable now. So, except for there's one rare instance where we use it in scientific notation, but we use a dot now for multiplying. So this means times -2. And then, of course, to go from -2 to +4, I would times by -2. And then to go from +4 to -8, I'm multiplying by -2 and multiplying by -2. And then hopefully everybody predicted, your conjecture was 16 times a -2 would take you to negative 32. Hopefully everybody had that. And if you did, you're doing pretty good. And then we got this challenge level one. Man, this one is a very important one. It's a pattern. Yep, it has a name. Some people call it a series or a sequence, but I put the 0 on there. It really makes it pop when you put the 0, 1, 1. That's not a righto, by the way. That is on purpose to have 1 and then another 1, 2, then 3, then it jumps up to 5, 8, 13. Again, pause and think on that for a little bit. And we're back. All right. Hopefully you all got 3 juicy predictions. Yeah, I didn't mention that. You're supposed to have the next 3 terms in this series or sequence. Hopefully you did. It took the kids here at school, they figured this one out pretty quick. And what it is, it's kind of hard to explain how to get to the next number, but kind of the best way to say it is to get to the next number, you add the 2 previous numbers. So 0 and 1, if you add those together, you get 1. And then if you add 1 and 1 together, you get 2. And 1 and 2 together, you get 3. So we're not just weirdly counting 0, 1, 2, 3 like that. That's why the double 1 is in there. But when you go 2 plus 3, that's how you get the 5. And 3 plus 5, you get 8. And 5 plus 8, you get 13. And then 8 plus 13, hopefully everybody's first prediction on this was 8 plus 13, you would get 21. And then 13 plus 21 is 34. And then 21 plus 34 is 55. So hopefully everybody predicted those 3 numbers. All right. Okay, how we doing? Everybody's doing good on time? Looks like I'm still recording. Good. It always makes me nervous. I get this deep in the lesson and I realize, oh, it stopped recording about 10 minutes ago. Oh, good. That hasn't happened. All right, moving on. Okay. Now, sometimes we have this interesting lesson on patterns and stuff, and they try to, sometimes even ham-handedly, try to bring it back to geometry, and that's what's going on in this second one. So they're straining kind of hard to tie this back to geometry, but, it's a geometry class, so we understand. But before we get to that one, they want us to make a conjecture about the sum of 2 odd numbers. So you need to know what sum means. I think most people know it means when you add. And odd numbers, those are those numbers that when you divide them by 2, they don't work out smooth. They leave you with like a decimal or a fraction. So those are the odd numbers, like 3 and 7 and 11, those kind of numbers. What would happen? What's your prediction? What's your conjecture about adding odd numbers? So one thing you can do is just do a few examples. Pick a couple of odd numbers, like maybe 3 and 1. You add those together, you'd get 4. Okay, 4 is a normal number. How about what if we have maybe if you add 5 and 3, those are odd numbers. You add 5 and 3, you would end up with 8. That's a normal number. But anybody notice anything about, I think what was the first one we got, 4 and then 8. Yeah, well, they figured it out pretty quickly in class today. Whenever you add 2 odd numbers, it doesn't matter if they're small, big, medium, close together on the number line, far apart on the number line, one positive, one negative, it doesn't matter. If you add 2 odd numbers, you will always get an even number. Always get an even number, all right? Hopefully everybody predicted that. All right, this one's kind of basic, and again, this is just the geometry book trying to, take this concept of patterns and predictions and whatnot and applying it to geometry. So what we've got here is we've got points A, B, and C are collinear. All right, one of our vocab words from last unit, meaning they're together on a line. So A, B, and C are together on a line. And then what if D is between A and B? What prediction could you make about D? All right, so A, B, and C are collinear, and then they're saying, okay, D is in between. What could you say about that? And there's nothing too amazing about it, but I'll just sort of give you a demonstration. So you got A and B and C on a line together. All right, they're collinear. And then they tell you that D is between A and B. So D's got to be anywhere in here, and it doesn't matter where I put D in between here. I could put it close to A, close to B, in the middle. It doesn't matter. I'll just put it right here. The conjecture they wanted you to make is that D would also be collinear. All right, so D is also collinear with A, B, and C. Nothing too surprising. That's just what they wanted you to get. Okay, then we got another vocab word. This is a pretty important one. It's called a counterexample. Is that like an example, Mr. Metcalfe? Sort of, but different. Counter means against. You've heard the phrase counterattack. That's like when somebody attacks you and you boom, you attack back. I mean, you don't just sit there and be on the defensive. You attack back. So it's when you go against something. All right. So a counterexample is different than an example. An example would be like when you're in elementary school and your teacher said, "Hey, somebody give me an example of a mammal," and you'd say something like maybe a bear or a deer or your dog or something. Those are all good examples of mammals. Then when you got to middle school, your teacher might have said, "Hey, we've been studying Native Americans. Somebody give me an example of a Native American tribe," and you might say Cherokee, Chickasaw, Seneca Indian, or was that an Indian? I think they were a type in. I can't remember, man. It's been a while. Cherokee, I think I said those already. Those would be good examples of Native American tribes. Well, a counterexample is a little bit different. All right, when somebody makes a statement in geometry, we initially assume that it's true unless we can come up with a counterexample, meaning an example that proves their statement is false. All right, that's what a counterexample is. It's not an example of something like a tiger is a mammal. It's like something that says, "Hey, you just made this statement, but this sort of proves that that's not true." And I've got a nice statement right here. If you go to Charlestown High School, then you live in Charlestown. And on the surface, or just a quick glance at that, you might say, "Oh, yeah, that sounds right." But when you start thinking about it, then you say, "Oh, wait a minute. I have this friend," or maybe you yourself live in Henryville and you go to Charlestown High School, or maybe you live in Sellersburg. We had several Sellersburg people today say, "Hey, I live in Sellersburg, but I go to Charlestown High School." So those would be instances of counterexamples. And counterexample is a very long word. I'm not going to write that again. We use the letters CE for counterexample. So a counterexample would be somebody who lives in any other town besides Charlestown, but they go to Charlestown High School. And like I've rattled off some, so, we got students who live in Jeffersonville who come here. We got students from Henryville, Otisco, all those little areas around here. But they come to Charlestown because we're the best. Yes. We're the best. Yes. Okay. So I'm just going to put a random example. We'll say Fred. Fred goes to Charlestown, but lives in, we'll say Sellersburg. All right, Sellersburg. I'll just call it Sburg. All right. So that would be a counterexample. Now, I didn't want to use a specific person's name, for this, but normally your counterexample would be something very specific, all right, a specific person. Okay, moving on. And that takes, oh wow, we are almost done, guys. We got a nice little statement. It says, if n is a real number, then n squared is greater than n. So you might be thinking, yeah, that sounds true. Yeah, when you square something, it always gets bigger, right? Not necessarily. All right. There are a few numbers that when you square them, they actually don't get any bigger. And spoiler alert, there's some numbers that when you square them, they actually get smaller. Yeah. And it took us a while, but every class came up with some good counterexamples because this statement is false. All right. So in geometry, you can't just say false, I'm out of here. No, if you say something's false, you got to be prepared to back it up with a counterexample. All right. So when somebody says this is false, the first thing I did is like, okay, why? And the two most popular answers we got for this today were 0 and 1. And I'll do 1 just to show you. So if your original number is 1, would 1 squared be greater than 1? And the answer is no, because 1 squared is 1 times 1 is 1. Is 1 greater than 1? No, 1 is equal to 1, so boom. So one counterexample would simply be the number 1. And then, like I said, a lot of people did the same thing with 0. But what was more exciting was when I told them, you know what, there's actually some numbers when you square them get smaller. And you know what everybody said, every class I think today said, well, negatives, right? Well, actually, no, negatives, like if I took a -7 as my original number and then I squared it, it would be positive 49, and everybody knows positive 49 is much bigger than -7. So not necessarily negatives. And then I threw out the example. Think of those numbers you hated back in the late elementary school, like 4th or 5th grade, and everybody's like, oh, fractions, yeah. And I said, what's the most popular fraction ever? And one even, everybody kind of understands, the most popular fraction is a half. If you got a brother or a sister, you understand the concept of a half, because there's that last cookie, that last donut or whatever, and your mom says, okay, you and your brother can have it. You got to break it in half. So everybody kind of understands the concept of half. But check out what happens when you take a half and you square it. It actually gets smaller, doesn't it? It's not going to be greater, because when you square a half, you've got 1 times 1 on top, which is still 1. I don't need that. Let's just write 1. And then when you square the bottom, 2 times 2, you got 4. Is 1/4 greater than the original 1/2? Absolutely not, man. Everybody knows that 1/4 of a pizza is way smaller than half of a pizza, right? If you only have 1/4 of a pizza, you're talking usually about 2 pieces, maybe 3 if it's one of those really big ones. But a half of a pizza is like 4 pieces or 6 pieces or something like that. So absolutely not. So a really good counterexample would be 1/2. Basically, any fraction in between 0 and 1 will actually make the number get smaller. All right, man, we are on the last screen, and I'm going to leave you with these. This was really fun. I'm not going to lie. In first period, they went crazy over these. I led off with the fact that you're going to get it wrong. I mean, I think the record is getting it right on 5 tries. I wish I would have wrote it down. I think first period it was probably close to 20 tries before we got it. And that's a really strong class. They jammed on that first test. So it had nothing to do with lack of mental ability. I mean, these are just tricky. I call these fun ones. They're really, I should call them frustrating fun ones. But I'll just leave these here with you. And again, if you figure them out, if you figure them out, and if you're an online person, want to send me an email, say, hey, I know what those next 3 terms and that one is. You'll probably be wrong unless you ask somebody, or if you've seen this before. Some people have seen this before. This one's good too. Once you find out the first one, then the second one gets a little easier, because you learn to think in a different way. So I'm not gonna lie to you. I've kind of led you down a path for patterns, and then I kind of do like a switcheroo on you for this. But here they are. If you can't read it, I'll just call them off. The first one is JFMAMJJA, and then I want to know what the next 3 would be in that pattern. And it's a pattern. It'll make sense when I reveal the answer, probably next lesson. And then this second one is OTTFFSE, and then I need the next 3 terms in that one as well. So that's it. That's the lesson. If you get those, if you want to shoot me an email, and just for fun, I'll tell you if you're right or wrong. But you've got an assignment. It was loaded up earlier today. And again, sorry about this lesson being loaded up a day late. Remember, submit your answers on the form, the Google Doc that says answers for worksheet 2-1. Send it on that one. Don't do something with the the one you can see, and some people, in the beginning that was fine. I don't have any problem with it, but now we want it to kind of be uniform. Everybody's submitting those documents to the same place, putting their period on there so that I know exactly where to put your grade quickly, and you'll see those grades popping in there much faster if we do that. So thank you. Don't get frustrated if you send things to the wrong spot. I've been getting, I get notifications, literally dozens of notifications that you all are submitting stuff late. Just be mindful when you do that. It's late, so it's gonna probably be late for me to grade it, but it will get graded. I promise you. I've never not graded people's papers that turned them in on time, not on time, but got them to me before the grading period was done. I've always do that. There will be a cutoff date at some point. Once we decide when that cutoff point is, boom, then I won't take stuff after that. But don't worry, it'll get graded. Maybe not as fast as you'd like it to get graded, but just keep in mind, if you turn an assignment in 10 days late, it makes sense that I would wait 10 days to grade it. I probably won't wait 10 days, but that would be fair, right? I mean, you turned it in 10 days late, I should get 10 days to wait. But I promise you, I almost never will do that. I'll grade them much faster than you turned it into me. But just be mindful of that. All right, I hope you have a great day, and I'll see you next time.